In Chapter 3, we're going to learn rules for differentiation so we don't have to use the limit definition for a derivative every time we need to find a derivative. So far, we have seen how to interpret derivatives as slopes and rates of change. We've seen how to estimate derivatives of functions given tables of values. We've learned how to graph derivatives of functions that are defined graphically. And we've used the definition of a derivative to calculate the derivatives of functions defined by formulas. However, it would be tedious if we always had to use the definition to calculate a derivative. So in this chapter, we develop rules for finding derivatives without having to use the definition directly. These differentiation rules enable us to calculate with relative ease the derivatives of polynomials, rational functions, algebraic functions, exponential and logarithmic functions, and the trigonometric and inverse trigonometric functions. We then use these rules to solve problems involving rates of change and the approximation of functions. So section 3.1 is how to find derivatives of polynomials and exponential functions. We start with the simplest of all functions, the constant function, f of x equals c. The graph of this function is, of course, a horizontal line, y equals c, which has a slope of 0. Therefore, the derivative of a constant must be 0, since a derivative is a slope, and we've already discussed that. If we were going to prove that, the formal proof is actually easy. We would prove it by using the definition of a derivative, which says the limit as h approaches 0 of f of x plus h minus f of x divided by h is equal to, in this case, 0 if f is the constant function. So if we evaluate the constant function c at x plus h, well, if it's constant, it's going to be c no matter what we plug in there. So we get c minus c, which is the limit as h approaches 0 of 0 over h, which is simply 0. And that's all there is to that proof. So we're using the limit definition, or in some cases, we're not going to look at the proof, but they're in the textbook, to prove all of these rules. And then once we do that, we can simply use the rule and not go back to the definition every time. If we were using Leibniz notation, we would use the d dx notation for the derivative instead of the f prime notation. Next, we're going to look at functions of the type f of x equal x to the n, where n is a positive integer, and we've already done several of these. If n equals n, the graph of f of x is f of x equal x, and it's the line y equal x, which is the identity function, and it has a slope of 1. So we would expect the derivative of the function x to simply equal 1, since again, derivative is slope. And you can also verify that equation from the definition of the derivative. And we've already looked at the cases where n equals 2 and n equals 3. In section 2.8, we found out that the derivative of x squared is 2x, and the derivative of x cubed was 3x squared. And in fact, I believe in class someone noted that perhaps there was a pattern here. And indeed there is. So far we have the derivative of just x, and remember this would be x to the first power, is 1. And the derivative of x squared is 2x. The derivative of x cubed is 3x. So we might guess that the derivative of x cubed is 3x squared, so we might guess the derivative of x to the fourth would be 4x cubed, and we would be correct. And in fact, if we take the derivative of any power x to the n, then we simply bring the exponent down and lower that value by 1 for our new exponent. So if we're going to do the derivative of x to the fourth, it would be 4x cubed. The derivative of x to the fifth would be 5x to the fourth. The derivative of x to the sixth would be 6x to the fifth. 7x to the sixth, and then the nth case would be nx to the n minus 1. So that's your pattern for finding a derivative if we have x to a power. And this gives us the power rule. If n is a positive integer, then the derivative of x to the n is nx to the n minus 1. So now henceforward, whenever you see a function x to the n, this is how you're going to take its derivative. If n is a positive integer and f of x equals x to the n, then in prime notation it looks like this. And the other slide was simply the Leibniz notation version of the power rule. We illustrate the power rule using various notations in example 1. So if f of x equals x to the 6th, then using prime notation, our derivative would be 6x to the 5th. If y equals x to the 1000, then again we're using prime notation but with y instead of f this time, and we should have 1000x to the 999th power. If y equals t to the 4th, then the derivative of y with respect to t, Leibniz notation, we get 4t cubed. Again, Leibniz notation, the derivative of r cubed with respect to r would be 3r squared. So several different ways we can indicate we want the derivative. F prime, y prime, dy dt, stating the function as y, or simply using the Leibniz notation and knowing that the function is what's going to be in parentheses here without having to state it separately. So what about power functions with negative integer exponents? What do we know about those? In exercise 61, we verified from the definition of the derivative that the derivative of 1 over x was negative 1 over x squared. Notice that you can write 1 over x as x to the negative 1, so it appears that the power rule is still working because we bring our negative 1 exponent down, and when you decrease negative 1 by 1, you'll get an exponent of negative 2. And we could rewrite this as negative 1 over x squared. So it appears that the power rule works whether n is a positive integer or a negative integer. In fact, in the next section, we're going to show that it holds for all negative integers. Well, what if the exponent is a fraction? And recall that fractional exponents mean roots. And in example 3 of section 2.8, we found the derivative of the square root function to be 1 over 2 times the square root of x. Well, we can write the square root as x to the 1/2 power, and if we bring the 1/2 down and then decrease 1/2 by 1, so 1/2 minus 1 gives us to the negative 1/2 power, which is just another way to write 1 over 2 times the square root of x. This shows that the power rule seems to work even when n is equal to 1/2. And in fact, in section 3.6, we're going to show that it's true for all real numbers, fractions, decimals, irrational numbers, rational numbers. It doesn't matter what those exponents are, as long as they're real numbers, the power rule works. So, in general, if n is any real number, then the derivative of x to the n is nx to the n minus 1. So if I had x to the 0.2, then its derivative would be 0.2 x to the negative 0.8. Doesn't matter what that exponent is. So that is cause for celebration because it's a lot easier to find the derivative that way than it is using the definition. So here's some examples. Let's differentiate these. In each case, we're going to rewrite the function as x to a power, so x to the negative 4. So then the derivative here would be negative 4x to the negative 5. And we can leave it like that, or if we don't want to leave negative exponents, we might want to rewrite that like that. The fifth root of x squared would be x to the 2/5, so that's just rewriting it as a rational exponent, and then the derivative would be bring the fraction or the exponent, whatever it is, down, and then 2/5 minus 1 would be negative 3/5. And again, we can leave that like that or go back to radical notation and get rid of the negative exponent by doing that. The power rule enables us to find tangent lines without having to resort to the definition of a derivative because it makes it a lot easier for us to find the slope. It also enables us to find normal lines. The normal line to a curve C at a point P is the line through P that's perpendicular. So normal in mathematics means perpendicular. In the study of optics, one needs to consider the angle between a light ray and the normal line to a lens. So find equations of the tangent line and normal line to the curve y equal x times the square root of x at the point 1, 1 illustrate by graphing the curve and these lines, and we'll pick up here in the next video.